To ECE CS 552, lecture on instruction sets with a focus on MIPS. The focus of this lecture will be on instruction set design. This is really going to be, in part, a review of 252 and 354. Instructions are the words of a computer. In other words, the instruction set architecture makes up the vocabulary that the processor is able to understand and serves to define the interface to the processor. Most of the interface. There are other things that also need to be defined that we'll touch on later. The advantage of having a fixed instruction set architecture is that the implementations that provide that functionality can and do vary over time. So for example, Intel processors have evolved from the 46 to the Pentium to the P6 to the Core Duo to the Core i7. The instruction set that we will be considering in this course is the MIPS instruction set, as well as a MIPS-like instruction set with small variants of it to be used in your project. The advantage of this type of instruction set is that it's simple, sensible, regular, and the CPU will be easy to design for these reasons, which is something you'll appreciate as you get into your project design. In contrast to this type of instruction set, the most commonly used instruction sets out there today, the x86 and ARM instruction sets, are not nearly as clean and straightforward and simple as MIPS. x86 is widely used in desktop PCs and laptops and servers, and ARM is widely used in cell phones and smartphones and other embedded systems. There are plenty of other instruction sets out there, like PowerPC from IBM or Spark from Sun, now Oracle. We're not going to be delving into the details of these other instruction sets. Instead, we'll just present MIPS and x86 as two examples at sort of two extremes of the continuum of complexity that exists in instruction sets. We're also not going to focus on software or writing programs in this course. So the purpose of reviewing instruction sets is to give you the proper context and review for talking about designing a processor that will then execute those instructions. Looking ahead, this lecture will cover some of the basics. We'll talk about registers, ALU operations, memory and load store operations, branches and jumps, and addressing modes. The basic idea behind an instruction set is to provide an interface to the hardware to implement the semantics of the program or algorithm that you're writing or wanting to execute. So for example, if you have a high-level language statement, such as the simple example shown here, where I'm adding G to H, adding I to J, and then subtracting the second sum from the first sum and storing the result in a variable F. We can basically convert this C statement into MIPS instructions that perform the two additions and the subtraction. You notice a few things going on here. First of all is that we are going to need multiple instructions for one single C statement. There isn't a one-to-one mapping there. In addition to that, we have to talk a little bit about the format of these instructions and what's going on here. So in the first column, in the left-hand column, you'll see what's called an opcode or a mnemonic. This is what specifies the operation to be performed. There are typically two forms that you'll see machine language or assembly language expressed. One is the human-readable textual form, such as what is shown here. So we have a textual identifier like ADD for add for the addition operation, SUB for the subtract operation. That would be the mnemonic. The actual underlying opcode is going to be the binary value assigned to represent that code or that operation. We also have operands. These are shown on the right-hand side. All three of the instruction examples here have three operands. These are used to specify the input and output data to the actual operation. Typically, by convention, the source operands will be shown on the right. So in this case, for the first instruction, G and H are the sources, and the destination will be shown on the left. In this case, it's T0. What's happening here in terms of the destinations is that T0 and T1 are not shown in the original C program. And the reason for that is that the C program is simply providing a single statement with a single assignment that we're now having to break up into multiple operations with multiple assignments. Since we really have nowhere to store the intermediate values, the sum of G plus H and the sum of I plus J, the compiler that converts the C language into the equivalent MIPS instructions now has to allocate space for these temporary values. That is what these T0 and T1 destination registers are in this case. Notice that in the final subtract, T0 and T1 then show up as the input operands for the subtraction. One question that might spring to mind is, why would we not specify bigger instructions? Why wouldn't we have a single instruction that performs the entire C statement. Well, this fundamentally goes back to Church's thesis proposed by a famous early computer scientists. The idea behind Church's thesis is that a very primitive computer is capable of computing anything that a fancy computer can also compute. All you really need are fundamental building blocks like logical functions, ways to read and write memory, and some data-dependent decision-making support. Once you have these basic primitives, you can use them to emulate any more complex computational operations as well. So for that reason, once you have that minimal subset, you can build more complex operations from that minimal subset. Any additions that you make to that minimal subset are really just going to be there for engineering reasons, because in the process of designing the computer, you've decided that to either improve performance or reduce cost or reduce power consumption, this new instruction will provide some kind of benefit in that realm. Now, one of the considerations that you have to keep in mind when you're designing an instruction set, when you're trying to determine which instructions to add and which ones to exclude, regularity is an important concept. So making your instruction set as regular as possible is going to make implementation of both the software tools that generate code for that instruction set, as well as design of the hardware that actually then implements that instruction set, more straightforward. So in this particular example, returning back to the statement at the top of the slide, we would need 4 input operands, G, H, I, and J. We would need 3 arithmetic operation specifiers for the 2 pluses and the minus, as well as 1 destination operand specifier for the result being stored into F. So we would have a very complicated instruction, and it would really only, that instruction would really only map to source code that happens to have this template. We might have a different statement in our C program that only has 3 operands and another one that has 6 operands, and so we'd be right back to having to break the more complex case into sequences of this case, even if it supported 4 operands, or conversely, for the simpler case, we would end up having to put in additions to zeros, so sort of redundant and useless operations to fill in the gaps to make it match this more complex template. So the generally accepted practice in this realm in industry is to go with 2 operand instructions, 2 sources, 1 destination, because those tend to be powerful enough to handle many common cases and simple enough to then use as a composable element to handle the more complex cases. In the MIPS instruction set, all arithmetic logic instructions, which are executed by the ALU or arithmetic logic unit, are required to have their source operands and destination operands stored in registers, not memory variables. So you see the earlier example here now where the inputs and the outputs are assigned to particular registers that are numbered and identified using the dollar notation. The MIPS instruction set provides the programmer with 32 registers numbered 0 through 31, and in this particular case we're using registers 8 and 9 for the temporary values T0 and T1. We're using 16 for F, 17 for G, 18 for H, and 19 for I, and 20 for J. MIPS also allows you to provide constant values as operands. These are called immediate values. We'll later see that because of the way the instructions are laid out in memory, this immediate value is going to be restricted to a maximum range or maximum precision of 16 bits. Pictorially, we can see that in the hardware, once we eventually design it, the arithmetic logic unit and the registers are going to be grouped close together so that we can quickly route register values to the ALU and can quickly route the results of the ALU computation back to the register file. Some other examples of ALU ops include adds, immediate adds, unsigned adds, subtracts, multiplies, divides, ands, ors, and shifts. SLLs and SRLs are left shifts and right shifts. One issue that comes into play here is that some arithmetic operations generate a wider result. You'll probably remember from decimal arithmetic that if you multiply 2-digit decimal numbers, you might actually end up with up to a 4-digit result. The same thing happens with the divide because you end up with a quotient and a remainder. So in effect, if we have a 32-bit instruction set with 32-bit registers, we could end up with a 64-bit product from the multiply and a 32-bit quotient and a 32-bit remainder from the divide. So some special case handling is needed. In this case, the way MIPS handles this is that there are special purpose registers that are defined to hold the results of multiplies and divides. These results do not go into the 0 through 31 general purpose registers that we've already discussed. So what is the main reason for using registers? Well, one of the main reasons is that the short name that we can use to specify a register fits comfortably in an instruction word. So for example, if we have 32 registers like we do in MIPS, we only need 5 bits to specify which of those registers is being accessed, which means with 5 bits per register, if we have now three registers, 2 sources and 1 destination, we're still only using 15 bits of space to store those specifiers. We'll see in a little bit how exactly these specifiers are laid out in instruction memory. Another question that arises when we talk about registers is, are they really enough? And of course the answer is no. If we write any kind of complex programs, we're going to need more storage space than that provided by the registers. Put another way, what we really need is a large memory. And typically the large memory is going to be laid out linearly in the address space and can be used to do things like store arrays of locations. Say we have an array M that's indexed by an index variable j. We want to be able to move data to and from these kinds of arrays, for example, and the way we do that is by using load and store instructions. So in the MIPS instruction set, again, we have support for these load and store instructions, where the load instruction specifies a destination register on the left, in this case register 17, and an address into the memory array on the right. And what that load instruction will do is go read that location in memory and store that result in the corresponding register. The store word instruction does the exact opposite. It'll take the contents of a register, in this case register 16, and store them in the memory location specified on the right-hand side. So to complete the picture, we can see we still have the processor with the ALU and registers on the left-hand side, but now we have a large memory on the right-hand side where our variables, in this case f and g, are stored at some location in that address space, in that memory. And of course, depending on the width of the address now that we're using to index into this memory, there will be some maximum memory location, which will be essentially 2 raised to the power of the number of bits of addressing. These load and store operations are very important for accessing arrays. In this example, we have an array A, and we want to access entry I in that array and increment it by the value H. We can do that by executing the 3 MIPS instructions that are shown in red. We can basically first load the value at a sub I, then add to it, and then store the resulting value back out to a sub I. And we can do this because we've preloaded some of the registers in our register file with appropriate values. For example, we've put the value of H into $18. We've already put I into register 21, and in the notation here, a start is a label, and it points to the beginning of address A, which in this case, address A is stored at memory location 8000. So once this code is actually converted to machine code, A start will be replaced with the immediate value 8000. We'll see a little bit more detail on how exactly this works in a little bit. MIPS also has additional load store instructions to deal with narrower data types like bytes and half words. Here again, we can then see how the example array A from the previous slide lays out in memory, where the first entry is at memory location 8000, the next location is at memory 8004, 8008, and so on. Now these values are incrementing by 4 because each entry in this array is not a single byte, but is actually 4 bytes making up a 32-bit integer. Next, we want to briefly discuss branches and jumps. Branches and jumps are the instructions that the MIPS instruction set and other instruction sets provide to enable us to implement control flow in the execution of programs that we write. So control flow derives from things like for loops and while loops, as well as if-then-else kinds of conditional constructs. So a simple example of a while loop is shown here, along with the corresponding MIPS instructions that implement that while loop. In this case, again, we assume that the 2 variables I and j are already preloaded into registers 8 and 9, and to perform the arithmetic operations shown, we have an add that adds j and I and stores the result in j, in this case assigned to, again, 9 and 8, registers 9 and 8, and then we have the immediate add instruction that increments register 8 by 1 in every iteration. At the end of the loop, we branch back up to the top to the label loop colon shown in the left-hand side of the example. And then at the beginning of every iteration, we perform the while check. So in this case, we will compare the values of registers 8 and 9. That's what the BEQ, or branch if equal, instruction does. And if the two values actually are equal, it will then branch to the label exit, which is at the bottom of the loop. So as long as the two values are not equal, we will continue iterating in this loop, performing the two adds and the jump back up to the top. Once the two values become equal, then we will exit. So you can see that the instructions on the right-hand side are semantically going to do exactly what is specified by the high-level language program on the left-hand side. So what does the branch equal really do? Well, it does really two things. It reads the two registers, 8 and 9, and it compares them. And then depending on the result of the comparison, it sets the PC either to the fall-through path, which in this case is just PC plus 4. PC, of course, is the program counter, which always points to the next instruction that you're going to fetch after you finish this instruction. Or if the comparison is satisfied, it'll set the PC to the target address, in this case, the exit branch, or the exit label at the bottom of the loop. We can also do comparisons other than equality or inequality. We want to do things like greater than or less than. In MIPS, we do these by using the BLT mnemonic. In this case, the BLT stands for branch if less than. As it turns out, the hardware doesn't directly support branch if less than. Instead, what that expands to is two instructions. Set less than, which is like an ALU operation. It uses the ALU to subtract the two registers 8 and 9 from each other, and then sets the equivalent of a flag, but stores that flag value into register 1. So the MIPS instruction set doesn't have any explicit flags like you might remember from the instruction set in 252. Instead, the results of a comparison like this are stored in one of the general purpose registers 0 through 31. Once that comparison has been performed, then a branch if not equal instruction can be used to examine the value that's in register 1, comparing that against a literal 0, and then if that comparison is either matched or mismatched, again the target instruction or the next PC value will be determined to be either the target or the fall through, just as it was in the earlier example. Now, one thing that you should be aware of is in the MIPS instruction set, when you refer to register 0, instead of there being an actual physical register that can contain an arbitrary value in it, register 0 is always hardwired to 0. So it's kind of a shorthand way of specifying an immediate value of 0 for these kinds of comparisons. But one of the restrictions that creates is that you can't then store any temporary values, or you can't assign any variables to register 0 either. So recapping, there are other MIPS branches like branch equal and branch not equal, and there are instructions for performing comparisons for less than or equal, greater than or equal to. We also want to be able to support unconditional jumps. Sometimes we just want to jump to a different address. Sometimes, like we saw in the earlier example, sometimes we actually want to jump to a location that's specified by a register to support computed jumps and virtual function calls. And sometimes we want to use a jump and link instruction. So the jump and link instruction has one special side effect. What it does is it takes the current next instruction value, which again is the current program counter plus 4, and stores that into register 31. And what this is doing for you is providing you the ability to jump somewhere and then return from that location sometime later. So this is very useful for function calls, where you might have multiple call sites for a particular function, and each of those call sites, of course, once the function completes, you want to return back to that call site, not to any different call site. And saving the return address in register 31 allows you to do that, because at the end of the subroutine, then you can simply jump register to register 31, which will return you back to the location that the call was made from, or the call site. The MIPS machine language itself then is expressed as 32-bit quantities that are stored in memory. So just to give you an example here, the add instruction, which has one destination register and two source registers, is laid out in that 32-bit memory location in machine language using the following bit encoding. Basically, the first 6 bits are used to specify the opcode. In this case, the opcode is all zeros. The next set of 5 bits from left to right is used to specify the first source. The next set of 5 bits is used to specify the second source, so that's why you see a 2 and a 3 there in binary. The next 5 bits is used to specify the destination, that would be register 1. And then the next 5 bits are unused for this particular instruction. And then finally, the final 6 bits are used to specify which specific ALU operation we want performed. So the operations are specified in 2 different opcode fields. On the left-hand side, we have 6 bits to tell us it is an ALU register to register type instruction. And on the right-hand side, we'll say of all the possible instructions that match that format, we want this particular one, which is a signed addition operation. This instruction belongs to what's known as the R format in the MIPS instruction set. There are basically 3 instruction formats that we'll cover in this lecture from the MIPS instruction set. The R format is the first of those. And basically here in the R format, we have 6 bits of opcode, 5 bits of the first source register, 5 bits of the second source register, and then 5 bits of the destination register, and then some additional fields as well as the function field that are specified for cases where the opcode itself simply identifies a set of possible functions that could be implemented or could be specified by that instruction. So just to avoid any confusion, don't think of these things as anything special. They're really just bits stored in memory. And if I were to load a particular instruction word using a load instruction into a register, I could treat it as a number. So for example, the encoding for add 2 to 3 and store the result in 1, shown on the previous slide, if interpreted as a 32-bit binary number, corresponds to the decimal number 4,392,976. So really these are just bits in memory, and the magic is in how they're interpreted. With stored program computers, instructions are represented as numbers, and they're only treated as instructions when they're fetched by our processor and interpreted as instructions. There are a number of other R format instructions for performing unsigned addition, subtraction, etc. We won't go through the details of those. They're covered in the textbook for your reference. The next instruction format we want to talk about briefly is the I format. This is used to encode instructions like the loads and stores that we talked about briefly earlier. In this case, the layout is a little bit different because we really only need 2 register specifiers, and we'd like to have an immediate value that's as large as possible. So what this instruction format does is it again provides you 6 bits to specify the operation through using a binary opcode, and then 2 5-bit fields to specify the 2 registers, and then the remaining 16 bits of the 32 are left to specify an immediate value. So we can specify up to a 16-bit value in binary to provide this offset that we're going to add to the register specified as the source register, in this case register 2 in this example. So this allows us to specify an address in memory that's anywhere plus or minus 2 to the 16th or plus or minus 2 to the 15th of the current value of register 2. The I format is also used for ALU operations that have immediate arguments. So for example, if I have an instruction that wants to add the immediate value 100 to register 2 and store the result in register 1, I can specify that using the binary encoding shown here for that instruction. One of the questions that arises here is how do we deal with constants that are larger than 16 bits? In other words, ones that fall outside the range shown on the slide here. Well, there's a special instruction that allows us to load the upper 16 bits of a register. That's the load upper immediate or LUI instruction shown here, where you can now specify the upper 16 bits using a much larger immediate field and place those into the upper half of the register. Then you can use an OR immediate instruction to load the immediate value specified by that instruction into the lower half of that register now. So between these 2 instructions now you're able to specify all 32 bits of a constant value and end up having that 32-bit value now stored in register 4. All of the loads and stores in the MIPS instruction set use the I format. The branch instructions also use the I format as shown in this example. The only difference is that the immediate offset field is treated a little bit differently. We take the 16-bit immediate offset and we actually left shift it by 2. Now the effect of that left shift by 2 is to turn that offset value into a word offset rather than a byte offset, since shifting left by 2 is equivalent to multiplying by 4, and there are 4 bytes per word. The final format we'll talk about briefly is the J format. The J format is used for jumps. There's a single opcode field, again, that's 6 bits wide, and then the remaining 26 bits are used to specify the target address for the jump. In MIPS, the address is encoded in a slightly weird format. Again, we don't specify the final 2 bits of the address, so that's why we concatenate 00 to the end of it as shown here, because all instructions are, again, 4 bytes long, and they're all aligned on 4-byte boundaries, so the lower order 2 bits will always be 0, so there's no reason to actually encode them into the instruction word. And then the 26 bits of the address that are shown here are not quite the full 32 bits, so we're going to then grab the missing 4 bits from the most significant bits of the current PC value. So this allows us to jump around a very, very large address space, but not quite the full 32-bit address space of this instruction set. Briefly summarizing the available instruction formats, we have the R format, the I format, and the J format. All specify a 6-bit opcode with an additional function specifier for the R format. And in the I format, instead of specifying 3 registers, you only specify 2 registers plus a 16-bit immediate. And in the J form, you simply use all 26 remaining bits after the opcode to specify the target address for the jump. Now, what does the instruction decoder have to do? It has to read these bits, a 32-bit chunk, out of instruction memory, and it has to then specify the control signals that are needed to actually execute the semantics of this particular instruction using the data path components that are in the data path. In subsequent lectures, we'll see exactly how this works, and in your project, you'll actually be implementing the combinational and sequential logic to accomplish exactly this task. One of the important things that has to happen to support high-level languages on top of one of these instruction set architectures is support for procedure calls. So procedure and function calls are commonly used in high-level languages, and typically an instruction set will be paired with something called an ABI, or application binary interface. The ABI is something that builds on top of the instruction set architecture to provide a standard way of making procedure calls. And the kinds of things that are specified as part of the ABI are how parameters are passed, which registers are saved and which are restored, how the procedure itself is called, where the results of a function are stored, etc. And there's a specific set of things that has to happen both for the caller, who is making the call to a procedure, as well as the callee, the procedure itself, has to do a certain amount of bookkeeping and busy work. And those things, again, include things like how do I deal with registers that may or may not be overwritten by the called function, how do I pass parameters, and how do I obtain the return address that I have to come back to. So all of this is pretty much just a software convention. The only real instruction set level support that we need is for the jump and link instruction, which we talked about a few slides back, because the jump and link is what gives us the capability to grab the return address when the call is actually made, so that then at the end of the call we can return back to that location. High-level languages also use what's called a stack to keep track of the procedure calls that are currently active. So every time a procedure call is made, a stack frame is allocated, and then if that procedure call in turn makes another procedure call, we allocate an additional stack frame, so the stack grows just like a stack of plates. Each stack frame is used again to pass parameters, return the return values, and also store the return address so that we know where to return to. Typically, the stack will grow from larger to smaller addresses, but this is actually completely arbitrary. By convention in MIPS, $29 is used as the stack pointer, and it's essentially pointing just beyond the last valid stack frame. If we want to push something onto the stack, again, we'll decrement register 29 and store to that location. If we want to pop, we'll load from an address based off of register 29 and then increment register 29 to basically deallocate that spot on the stack. Just to make this a bit more clear, here's an example of a procedure. We have a procedure called swap that takes 2 arguments. and swaps one of them, which is an array, a pointer to an array V, and one is an index. And what we want to do is basically swap locations k and k plus 1 in that array, which is what the C code shown does. Again, to enable this or to implement this in MIPS, we're going to assume that $4, which is the first parameter, is passed in through register 4. $5 is k, so register 2, or argument 2 comes in through register 5. And then we're going to use 8, 9, and 10 as temporaries that, according to our application binary interface, or ABI, the callee can use without saving. So some registers have to be saved by the callee, others are fair game. You can use them without having to worry about restoring their values. In this particular ABI that we're using for this example, 8, 9, and 10 are temporary, so they don't have to be saved. They're caller saved. So whoever calls this function, if they have values in 8, 9, and 10 that they want to maintain, they'll have to save them somewhere else and then restore them after the call. So what's happening here is, first of all, we see the 3 instructions at the top are essentially computing the address that corresponds to entry k of array V. And there's a little bit of trickery going on here. Normally we would expect to see a multiply here because k is specified as an integer value, and to turn that into an index into an array of integers, we'd have to multiply it by 4. Now, multiply is a relatively expensive operation, so what's happened here is the compiler has actually converted the multiply into 2 adds, because we can actually implement a multiply by 4 with this sequence of adds. We can basically add k to itself, that's essentially equivalent to multiplying by 2, and then perform a self-addition of that 2k value now to go from 2k to 4k, and that leads us to having the value k times 4 in register 9 after the second instruction. The third instruction then adds that offset now to the value of V, which is the address of the first entry in the array V. So at the end of the third instruction, we now have the address of entry k of array V in register 9. After that, we just simply see 2 loads and 2 stores, which are loading the value v sub k, loading the value v k plus 1, and then storing them into the opposite location to implement the swap. And finally, at the end, we have a jump register to register 31, which returns us back to the call site. So one of the tricky things that happens here is that even though in our high-level language we declared a variable temp, we actually never see a memory location allocated for that variable. And the reason for that is that we don't really need it. Instead of using a temporary value, we're simply using temporary registers 8 and 10 to store the 2 memory values that we loaded with the 2 loads and then stored with the 2 stores. So we avoid actually allocating any memory for that temp variable. We can simply use a register to accomplish that task. We'll close this lecture out by introducing the concept of addressing modes. Addressing modes are an important attribute of an instruction set architecture because they are essentially the way that the instructions can specify the operands that are needed for whatever operation is being performed. And there are many different possible addressing modes. MIPS only supports a small handful. Other instruction sets support many more. We'll see a few examples of those in the next lecture. The most straightforward addressing mode is the register addressing mode. We've already seen many examples of this where we simply include a field in the instruction. In the case of MIPS, these are 5-bit fields that specify a register number, and we access the operand simply by indexing into the register file at that offset. The second addressing mode we've also seen examples of already is base plus displacement addressing. So the idea here is that we read a register value, in this case register 2. We also read a number of immediate bits out of the instruction itself. We add those 2 values together, and that forms an effective address that we then use to index into memory and access the corresponding entry in that memory location. We've also seen an immediate addressing mode. In this particular case, an add immediate instruction, again, simply reads the immediate field out of the instruction word itself and then adds that immediate value to the register source and stores the sum in the register target. We've also seen a PC relative addressing mode where we read some immediate fields or read an immediate field out of the instruction word itself. We read the current value of the program counter, and we add the two together to generate an effective address into memory. This is what the branch instructions in MIPS use. Summarizing today's lecture, there are basically very many options, a large set of options available to a designer when you're designing a new instruction set architecture. The downside of this, of course, is that backwards compatibility typically severely limits your options as a designer. It's very rare to have the luxury of designing an entirely new instruction set. So if you're designing extensions to an existing instruction set, you have to be very wary of making changes to the encodings and changes to the instruction set that break existing programs that relied on a previous definition of the ISA. In general, when designing an instruction set, keeping it simple and regular will make the designer's life easier. It'll also make the programmer's life easier. Any programmer that's either writing assembly code directly or who's writing a compiler that has to generate machine code from a high-level language will have an easier job of it if the instruction set is simple and easy to understand. The kinds of things you want to keep simple and regular are keeping the instructions a constant length, keeping the fields in the same place, and so on. However, an efficient encoding also has the advantage of minimizing the memory footprint. So if you can find a way to specify the semantics of the instructions using fewer bits, you will consume a smaller amount of instruction memory and end up with a smaller program overall. But that has limitations because if you reduce the number of bits to specify a register operand, for example, you end up having fewer registers. And so you end up being able to store fewer variables in registers. You end up having to access more variables to and from memory. And so you may end up actually increasing the size of your program because of the additional load and store operations required to move operands between the register file and memory. In general, compromises are inevitable. One of the key things that one has to pay attention to is when adding features or designing features into an ISA, pipelining or efficient implementation of that instruction set in hardware should not be hindered, if possible at all. So this is an important consideration, which drove a lot of the design decisions in the MIPS instruction set, as well as some of the other instruction sets that were designed more recently than, say, the x86 instruction set. And a final guideline to follow, which again derives from Amdahl's law, is to optimize for the common case. So you don't want to add a new instruction set that requires a lot of changes to either your software or to your hardware if in fact that instruction is expected to be used very rarely. You should optimize for the kinds of operations that are commonly performed and that are the common case.